Hello, everyone. Welcome to today's presentation. I'm excited to have you here. We'll be exploring Chapter 3, focusing on AWT and SWING. This is a fundamental part of understanding Java's graphical user interface components. Over the next few slides, we'll cover the basics, compare AWT and SWING, and discuss their uses and differences. Let's get started. Let's take a closer look at the GUI, or graphical user interface. The user interface, or UI, is essentially the space where humans and machines interact. It's where we communicate with the system and also receive feedback. The main goal here is to make this interaction as effective as possible, so users can operate and control the machine easily. And at the same time, the machine provides feedback, information that helps us make better decisions. Now, there are two main types of user interfaces. First, we have the command line user interface, or CLI. This is where users type in commands in text form, line by line. It was the primary way we interacted with computers for many years. But then, the graphical user interface, or GUI, came along and revolutionized how we work with machines. A GUI uses visual elements like icons, windows, and menus, making it more intuitive and user-friendly. This shift greatly improved accessibility and efficiency, which is why GUIs are now the dominant way we interact with most devices today. Understanding these types helps us see how user interfaces are a key part of making technology more approachable and effective for everyone. Let's talk about GUI, or graphical user interface. Essentially, a GUI provides a way for users to interact with a program through visual components. For example, an operating system offers a GUI with elements like windows, dialogues, buttons, text fields, text areas, list boxes, combo boxes, labels, checkboxes, and more. These are what we call GUI components. Using these components, we can build an interactive and user-friendly interface for any application. Think of a GUI as presenting a pictorial interface to a program, making it more accessible and easier to use. It also gives the program a distinctive look and feel, which can really enhance the user experience. All these GUI components are built from what we call controls or widgets. Essentially, a GUI component is an object that the user can interact with, whether that's clicking with the mouse, typing on the keyboard, or using other input methods. So, in summary, a GUI is all about creating an engaging visual environment using these components, making software more intuitive and accessible for everyone. Let's take a closer look at the Java Foundation classes, or JFC. The JFC is essentially a set of libraries that help programmers create robust enterprise applications using Java. It's designed to simplify and streamline the development process by providing a comprehensive toolkit. The JFC is made up of 5 main components. First, there's AWT, which stands for Abstract Window Toolkit, and it's the foundation for building graphical user interfaces. Then, we have SWING, which is built on top of AWT and offers more sophisticated and flexible UI components. Accessibility support is integrated into SWING, ensuring that applications can be used by everyone, including users with disabilities. Next, there's Java 2D, which has become an integral part of AWT. Java 2D allows for advanced graphics and image manipulation, enriching the visual capabilities of Java applications. Finally, there's drag and drop support, enabling intuitive user interactions by allowing users to easily move objects within the application. It's important to note that these 5 parts are interconnected. They're not mutually exclusive. In fact, SWING is designed to work seamlessly with AWT, and future Java versions aim for even deeper integration between these components. This interconnectedness makes AWT the core of the JFC, highlighting its significance. Overall, the JFC plays a vital role in Java 2, providing developers with powerful tools to create visually appealing, accessible, and user-friendly enterprise applications. Understanding how these parts work together helps us leverage the full potential of Java for complex application development. Let's talk about the accessibility package first. It provides essential support for users who might find traditional user interfaces challenging. This includes tools like audible text readers or braille keyboards, which help users access Swing components directly. These tools ensure that everyone can interact with the interface effectively, emphasizing the importance of inclusive design. Moving on, the 2D API is quite powerful. It offers classes that let us implement various painting styles, create complex shapes, and choose different fonts and colors. This flexibility allows us to craft more visually appealing and distinctive interfaces, enhancing user experience. Now let's consider drag and drop, or DND, which is a common metaphor we see in many graphical interfaces today. It allows users to click on an object, hold it, and then move it to another window or frame. The key here is that this process is predictable, making interactions intuitive and natural. All these features, accessibility, advanced graphics, and intuitive interactions, tie back to our overall goal: creating user interfaces that are accessible, visually rich, and easy to use for everyone. JFC. When we talk about GUI components in Java, there are two main sets to keep in mind: the Abstract Window Toolkit, or AWT, and SWING. Both of these are part of the larger Java Foundation classes, or JFC, which provide the building blocks for creating user interfaces. Now, the original Java GUI was called the AWT, and it served us well initially. But over time, developers encountered performance issues and limitations in extendability with AWT. To address these problems, Swing was introduced as a new GUI interface. Swing essentially offers replacements for most of the AWT components, making GUIs more flexible and powerful. That said, many of the non-component classes from AWT are still in use today. Recognizing the evolution from AWT to Swing helps us understand how Java's GUI capabilities have improved over time, enabling us to build more responsive and feature-rich applications. AWT, which stands for Abstract Window Toolkit, is the fundamental GUI toolkit that comes with every version of the Java development kit. It's essentially a collection of classes designed to give developers everything they need to build graphical interfaces for Java applets or applications. Think of it as Java's way of handling the visual part of your programs, creating windows, buttons, and other user interface components. Most of these components are built upon a core class called Java AWT component, which provides the basic functionality for all visual elements. This means that when you're working with AWT, you're working with a set of tools that are both powerful and consistent across different platforms. Overall, AWT is a key part of Java because it's specifically designed for creating user interfaces and painting graphics and images. It helps us craft visually engaging applications while maintaining platform independence. As we explore more about Java's GUI capabilities, keep in mind that understanding AWT is fundamental to mastering how Java interacts with users visually. Components are the fundamental elements of a graphical user interface, or GUI, and they can also be called controls or widgets. These are the building blocks that users interact with, like buttons, text fields, and labels. Understanding these components is essential because they make up the visual and interactive parts of any application. Now, if we look at Figure 1.1, it provides a hierarchical view of some of these AWT components. This hierarchy helps us see how different elements are related and organized within the framework. Recognizing this structure is important because it allows us to understand how components are classified and how they work together to create a cohesive interface. By exploring these components and their relationships, we get a clearer picture of how GUIs are constructed and how we can manipulate them to build more effective and user-friendly applications. This understanding forms a core part of our overall theme, creating intuitive and functional user interfaces. Now, let's take a closer look at the major components you can work with in the AWT. First, we have the button, which is simply a push component that users can click to trigger actions. Next is the canvas, a versatile component that allows you to paint and create custom graphics, making it ideal for drawing or visualizations. Then there's the checkbox, which can be in an on or off state. It's often used in groups where only one checkbox can be checked at a time, helping with option selection. Moving on, the choice component allows users to select one option from a group of choices, functioning as a drop-down menu. We also have the label, which is a static string displayed at a specific location, useful for titles or descriptions. The list component presents a list of items that users can scroll through, perfect for selecting from multiple options. The text area allows for multiple lines of text, making it suitable for larger input or display areas. Text fields are single-line input areas, commonly used for user data entry like names or search queries. Lastly, the container is a special component that can hold other components. Think of it as a container or panel that organizes your interface, whether that be a window, a frame, or an applet. Understanding these components is fundamental because they form the building blocks of any AWT-based user interface. They help us create interactive, user-friendly applications that are both functional and visually organized. Let's take a closer look at AWT and its top-level windows. First, we have the window, which is a top-level window without any borders. It's useful when you want a plain, undecorated window for your application. Then, there's the frame, another top-level window, but this one comes with borders, title bars, and controls like minimize, maximize, and close buttons, making it more like the standard application window we're used to. Next, we have the dialog. These are special top-level windows used to create dialogues that interact with the user, like alerts, confirmations, or input prompts. One common subclass of dialog is the file dialog, which allows users to browse and select files. These dialog windows are essential for user interaction and information exchange. Moving on, we have the panel. Unlike the previous windows, a panel is a subclass of the container class and is used to organize or group collections of objects within a window. What's important to note is that panels don't create their own separate windows. Instead, they serve as a way to organize content inside other windows, making the GUI more manageable and structured. So these different top-level windows help structure our applications effectively, providing various ways to interact with users and organize content visually. They are fundamental building blocks in creating intuitive and well-structured GUI applications with AWT. Swing emerged as a response to the limitations of AWT, which many developers found lacking in flexibility and modern features. Sun Microsystems recognized these shortcomings and committed to delivering a more robust and versatile solution in future Java releases. To do this, they had to develop a brand new class library, one that could address the needs for more advanced and customizable GUI components. This new library eventually became known as Swing. It included all the advanced classes that developers now expect for building rich user interfaces, from simple labels to complex components like tables, trees, and styled text documents. While Swing isn't perfect and still has room for improvement, it represented a significant technological leap forward from AWT. One of the most notable aspects of Swing is its extensive set of components. These range from the very simple, like labels, to the highly complex, such as tables, trees, and styled text documents. This flexibility allowed developers to create much richer and more interactive applications, aligning with the overall goal of making Java a powerful platform for desktop applications. Swing, as you can see, almost all Swing components are built upon a single parent class called JComponent. Now, JComponent itself extends from the AWT container class. This is a key point because it shows that Swing isn't a completely separate framework. Rather, it's layered on top of AWT. So, in a way, Swing acts more like an enhancement or a new layer that adds more functionality and flexibility to the existing AWT components. You'll notice that for each AWT component, there's usually a Swing equivalent that starts with the letter J, like JButton, JText field, or JCheckbox. These are designed to be familiar, but with additional features that Swing offers. An important exception here is the AWT Canvas class. Unlike the others, it doesn't have a direct Swing counterpart. Instead, you can use components like JComponent, JLabel, or JPanel as replacements, depending on what you need to do. Overall, understanding this hierarchy helps clarify how Swing fits into Java's GUI toolkit. It's built on top of AWT, but provides a richer, more flexible set of components for building user interfaces. Let's talk about swing components. Generally, these components usually start with the letter J, which helps us identify them easily. Most of these components are lightweight, meaning they are written entirely in Java, making them more flexible and easier to integrate. However, there are a few exceptions, such as Japlet, JFrame, JWindow, and JDialog, which are not lightweight and have some differences in their implementation. It's also important to note that for nearly every AWT component, there is a swing equivalent or analog. This means that Swing often provides more modern and versatile options that build upon the foundation of AWT components. Understanding this relationship helps us to create more sophisticated and responsive user interfaces in Java. Overall, knowing these key points about Swing components will help us choose the right tools for our GUI development and leverage the power of Swing in our applications. Let's take a look at how AWT components are mapped to Swing components. Essentially, almost all of the AWT classes get a J prepended to their names when we switch to Swing. For example, the AWT button becomes JButton in Swing, and similarly, a panel turns into JPanel. The list component in AWT is replaced by JList in Swing. Now, there are a few exceptions to this pattern that are worth noting. For instance, the AWT checkbox becomes JCheckbox in Swing, and you'll notice that the case changes here. It's more than just adding a J. Another example is Choice, which maps to JComboBox in Swing. The key takeaway is that this nomming pattern helps you identify Swing components easily by their J prefix, making the transition from AWT to Swing more intuitive. It also highlights that while most components follow this pattern, some exceptions have specific nomming conventions to remember. This understanding is crucial as we build more complex interfaces, ensuring we're using the correct Swing components instead of their AWT predecessors. Now, let's take a look at some new components that can really enhance our user interfaces. First up is the JTree. This component allows us to create a hierarchical tree structure where nodes can be expanded or collapsed, making it perfect for representing nested data like file systems or organizational charts. Moving on, we have the JTable, which is used to display data in a tabular format. Think of it as a flexible way to show database results or spreadsheets within our applications. Next, let's talk about tooltips. These are small pop-up texts that appear when the user hovers over a component. You can add them easily with the setTooltipText method, and they work with any J component. For example, if you have a button, adding a tooltip can give users quick hints about its function, like press to quit on a quit button. Another useful component is the J pop-up menu, which appears when a user right-clicks on a component, giving context-sensitive options. This is great for providing additional commands without cluttering the interface. Finally, we have the JOptionPane class. It offers static methods to display modal dialogues that grab the user's attention. Commonly used methods include showMessageDialog for simple messages, showConfirmDialog for yes-no questions, and showInputDialog to gather user input. These are essential for creating interactive and user-friendly applications. Overall, these components expand our toolkit, allowing us to build more dynamic, intuitive, and engaging interfaces. Let's talk about where to declare components in your code. Components are usually declared in one of a few key places. First, there are field variables, which are also known as instance or member variables. These are the best choice for components that you need to reference after your interface is built, like text fields, text areas, checkboxes, and so on. Next, there are local variables. These should be used for components that you won't need to access later, after the interface is constructed. For example, panels that hold other components or buttons that are mainly interacted with through their listeners. And finally, there's anonymous creation. This is common with labels, where you create and add the label in one step without ever assigning it to a variable. It keeps things concise when you don't need to reference the label later. So, understanding where to declare each component helps keep your code organized and efficient, aligning with how you plan to use those components throughout your interface. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at Figure 1.3, which provides a description of some basic Swing components. As we explore this, keep in mind that these components are the building blocks for creating user interfaces in Java. They each serve a specific purpose and are fundamental to designing interactive applications. You'll notice how each component has its unique role, whether it's for displaying text, accepting user input, or providing controls. Understanding these basics is essential as we move forward because they form the foundation for more complex GUI design. So, as we go through this figure, think of it as familiarizing yourself with the vocabulary you'll use throughout your Java Swing projects. This knowledge helps you connect the dots between the components and how they work together to create a seamless user experience. So, in this example, we're looking at a simple GUI-based input and output using JOption pane. Now, most applications we use daily, like email clients or messaging apps, rely heavily on windows or dialog boxes to interact with us. For instance, when you compose a message in an email program, you're typing into a window that the application provides. Those windows are what we call dialog boxes, and they serve an important purpose. They can display messages that are important or critical, or they can prompt us to provide information needed for the program to function. Now, Java's JOption pane class, which is part of the JAVAX Swing package, makes creating these dialog boxes straightforward. It offers pre-built, ready-to-use dialog boxes for both input and output purposes. The key is that you invoke static methods directly from JOption pane to display these dialogs. In this slide, there's a simple example of an addition app. It uses two input dialogues to ask the user for numbers, and then it shows the sum in a message dialog. This demonstrates how easy it is to gather input and display output using JOption pane, making your applications more interactive and user-friendly. Overall, understanding how to use JOption pane helps us build more engaging interfaces, which ties into our broader goal of creating effective user interactions in Java applications. Let's look at example 1. Here, we see a practical application of the concepts we've been discussing. This example highlights how the key principles can be translated into real-world scenarios. Notice how the approach taken addresses the specific challenges faced in this situation, emphasizing the importance of tailoring solutions to context. It also demonstrates the effectiveness of the strategies we've covered, reinforcing the overall message of the presentation. By examining this example, we can better understand how to implement these ideas in our own work, ensuring we stay aligned with the overarching themes of innovation and adaptability. Let's take a look at example 1, which is shown in Figure 1.4. This example demonstrates an addition program that uses JOption pane for both input and output. Now, what makes this interesting is how it simplifies user interaction by popping up dialog boxes instead of relying on the console. This approach makes programs more user-friendly, especially for those who prefer graphical interfaces. In this example, the program prompts the user to enter two numbers through input dialog boxes. It then performs the addition and displays the result in a message dialog box. This highlights the key concept of how JOption pane can be used seamlessly for both getting input and showing output, making your programs more interactive and visually appealing. Connecting this to our overall theme, this example underscores the importance of using GUI components to create more engaging applications. It also shows how you can incorporate simple dialogues into your programs, making them more accessible and easier to use, especially for users unfamiliar with command line interfaces. Let's talk about Swing versus AWT and what that means for look and feel. Back in Java's early days, GUIs were built using components from the Abstract Window Toolkit, or AWT, which is found in the Java AWT package. Now, what's interesting about AWT is that its components actually look like the native GUI elements of the operating system where your Java program is running. For example, if you run a Java application on Windows, the button component will look just like other Windows applications buttons. On a Mac, it looks like a Mac button. This native appearance helps create a seamless user experience, but it also means that the way you interact with these components can differ from one platform to another. This combined appearance and interaction style is what we call the look and feel. So, when we talk about look and feel, we're referring not just to how the component looks visually, but also how users interact with it. This is an important concept because it impacts the consistency and usability of your applications across different platforms. Understanding this helps us see why newer GUI frameworks, like Swing, were developed to give developers more control over the look and feel, making applications more portable and consistent regardless of the operating system. Swing versus AWT. Swing GUI components give you the flexibility to set a consistent look and feel across all platforms, or even to customize the appearance for each specific platform. This means you can create a uniform user experience no matter where your application runs, or allow users to choose their preferred style by changing the look and feel during runtime. Now, let's talk about the difference between lightweight and heavyweight components. Most Swing components are lightweight, which means they are written, manipulated, and displayed entirely in Java. This makes them portable and easier to manage, since they don't depend on the underlying platform's windowing system. On the other hand, AWT components are heavyweight because they rely on the local system's windowing environment to determine how they look and behave. This dependence can sometimes lead to inconsistencies across different platforms. And to clarify, only a few Swing components are heavyweight, since Swing was designed to be lightweight and more flexible. Understanding these differences helps you make better choices when designing your application's GUI, especially if you want a consistent appearance or need platform-specific features. Generally, when we compare AWT and Swing, the concepts are quite similar. AWT tends to be more portable across different platforms, while Swing offers a more modern and appealing look. One of the key differences is how they handle layout. AWT can be inconsistent depending on the operating system, which can lead to some layout issues. Most of the older AWT code can be easily adapted to Swing by simply adding a J in front of the class names. For example, changing button to JButton. AWT relies on peer components provided by the underlying OS, which makes them heavyweight components. This means they depend heavily on the native OS's implementation, which can affect consistency and performance. Swing, on the other hand, introduces a lot of new, user-friendly features like tooltips, mnemonics, borders, and dialogues such as J-option pane. These make building interfaces easier and more flexible. In fact, Swing is mostly written in Java, about 99%, and uses lightweight components, meaning they don't rely on the native OS components. This results in a more uniform appearance across different systems. Speaking of layout, Swing handles it consistently on all operating systems, which is a big advantage if you want your interface to look the same everywhere. Finally, Swing still uses AWT's event handling system, so you get the best of both worlds, modern features with reliable event management. Overall, understanding these differences helps us choose the right toolkit for our application, balancing portability, appearance, and ease of development. Generally, AWT and Swing are both used for creating graphical user interfaces in Java, but they have some important differences. Unlike AWT components, which are built using platform-specific code, Swing components are written entirely in Java. This means they are platform-independent, making your applications more portable across different operating systems. The term lightweight is often used to describe Swing components because they don't rely on the native GUI elements of the underlying platform. Instead, they are rendered in Java, giving you more control over their appearance and behavior. Swing provides replacements for most of the AWT components, which helps modernize your user interfaces, though many AWT non-component classes are still in use for certain functions. Importantly, Java ensures upward compatibility, so your existing AWT components will generally continue to work even when you incorporate swing. However, it's crucial to be cautious when mixing swing and AWT components in the same interface. Doing so can lead to errors or unexpected behavior, so the best practice is to decide early on which framework to use for your project. Overall, understanding these differences helps you choose the right tools for creating robust, platform-independent GUIs in Java. Let's take a closer look at the advantages of Swing and AWT. Generally, Swing offers some significant benefits. For instance, Swing is faster, which means it can deliver a smoother user experience. It's also more complete, providing a richer set of components and capabilities to build modern interfaces. Plus, Swing is actively being improved, so it continues to evolve and incorporate new features. On the other hand, AWT has its own strengths. One key advantage is that AWT is supported on older browsers as well as newer ones, so applets written with AWT are more likely to run across a wider range of environments. Additionally, the Java Micro Edition, or Java ME, which is used for devices like phones, TV set-top boxes, and PDAs, relies on AWT instead of Swing. This makes AWT particularly relevant for applications targeting embedded and mobile devices. Understanding these differences helps us see how each toolkit fits into different development scenarios and highlights why choosing the right one depends on the specific requirements of our project. Generally, AWT and Swing are the foundational tools we use to create graphical user interfaces in Java. When we look at the core of these systems, the class component in the Java AWT package stands out as a superclass. This means it defines the common features that all GUI components share, whether they're from Java, AWT, or JAVAX, Swing. It's like a blueprint that ensures consistency across different types of components. Any object that is a container, which is also part of Java, AWT, can be used to organize other components. Think of a container as a kind of holding space where we attach various components, like buttons or text fields, to build our interface. And an important point is that containers can be nested within other containers. This nesting allows us to organize a complex GUI in a hierarchical manner, making it more manageable and visually appealing. Now, when we talk about Swing, the class JComponent in JAVAX, Swing is a subclass of container. This means JComponent inherits all the organizational capabilities of a container, but also adds its own features tailored for Swing components. So, in the broader context of our presentation, understanding these class relationships helps clarify how Swing builds on AWT's foundation, offering more flexibility and consistency in designing GUIs. Generally, AWT and Swing are both part of Java's GUI toolkit, but they serve different roles. Swing is built on top of AWT, providing more sophisticated and flexible components. Now, if we look at Figure 1.5, we see how these components are organized in the class hierarchy. Central to this structure is the JComponent class. It acts as the superclass for all lightweight Swing components, meaning that it declares the common attributes and behaviors shared across these components. Because JComponent is a subclass of container, it also inherits the ability to hold other components. This makes all lightweight Swing components not only visual elements, but also containers that can organize other components inside them. Understanding this hierarchy is key because it highlights the flexibility and reusability of Swing components. They share a common foundation, which simplifies development and enhances consistency across the user interface. So, in the broader context of our presentation, recognizing how these classes relate helps us better understand how to build complex, yet manageable, GUIs in Java. Generally, AWT and Swing provide a rich set of features to create flexible and user-friendly interfaces. When working with JComponent, there are some common features that really enhance the user experience. One key feature is the pluggable look and feel, which allows you to customize the appearance of your components to match different platforms or themes. This helps make your application look consistent and professional across various environments. Another important aspect is shortcut keys, often called mnemonics. These enable users to access GUI components directly through the keyboard, making navigation quicker and more accessible. Tool tips are also very useful. They provide brief descriptions of what a component does. When a user hovers the mouse over a component for a moment, the tool tip appears, offering helpful guidance without cluttering the interface. Support for accessibility is crucial too. For example, Braille screen readers allow visually impaired users to interact with your application effectively, ensuring inclusivity. And finally, support for localization means you can adapt your user interface to different languages and cultural conventions. This makes your application more versatile and ready for a global audience. All of these features come together to make Swing a powerful toolkit for creating interfaces that are not only functional, but also adaptable and accessible for everyone. Let's take a look at example 2, which focuses on displaying text and images in a window. Most windows you create with Swing will contain GUI components, and these are typically instances of the JFrame class or one of its subclasses. JFrame serves as the main window container and is an indirect subclass of Java, AWT, window, meaning it inherits the basic window features. When you create a JFrame, it automatically provides essential elements like a title bar at the top and buttons to minimize, maximize, or close the window. Now, moving on to labeling GUI components, it's common practice to add descriptive text to help users understand the purpose of each element. This is where labels come into play. Labels are created with the JLabel class, which is a subclass of JComponent. Think of a JLabel as a simple way to display static content. It can show read-only text, an image, or even both at the same time. Overall, understanding how to effectively use JFrame and JLabel is fundamental in building user-friendly interfaces. They form the foundation for creating windows that are not only functional, but also clear and visually organized for the user. Let's take a closer look at Figure 1.6, which shows JLabels with text and icons. As you can see here, JLabels are versatile components in Java Swing that can display both text and images. This flexibility allows us to create more engaging and informative user interfaces. Notice how some labels contain only text, some only icons, and others combine both. This combination can be used effectively to convey information more visually, making your application more intuitive. For example, pairing an icon with descriptive text can help users quickly understand the purpose of a button or a status indicator. Understanding how to customize JLabels with icons and text is key to creating professional-looking GUIs. It ties into our overall theme of building user-friendly interfaces by leveraging these components creatively. So, keep in mind that mastering JLabels with text and icons will give you more control over how your application's information is presented to users. Let's take a closer look at Figure 1.7, which shows a test class for label frame. Here, we're demonstrating how to effectively test a label frame widget in our GUI. The key point is understanding how the test class is structured to ensure the label frame functions as expected. Notice how the test isolates specific functionalities, making it easier to identify issues. This approach highlights the importance of thorough testing in GUI development, which is essential for creating reliable and user-friendly applications. Connecting this to the overall theme, it's a reminder that good design isn't just about how the interface looks, but also about ensuring it works seamlessly through proper testing. When building a GUI, the first step is attaching each component to a container, like a window created with a JFrame. This ensures that all your elements are organized within a main container. Once you've done that, you need to decide where to place each component on the screen, a process known as specifying the layout. Java offers several layout managers that help you position components effectively, so you don't have to manually set every pixel. Many IDEs also come with visual design tools. These tools let you specify the exact sizes and positions of your components using a mouse, and then they automatically generate the underlying GUI code for you. This can be a huge time saver and makes the process much more intuitive. Remember, Java's layout managers are key for sizing and positioning components consistently and neatly. They help you create GUIs that are both functional and visually appealing, fitting into the overall theme of building user-friendly interfaces. Now, let's talk about specifying the layout. When we use the Flow Layout Manager, components are placed on a container from left to right in the order in which they're added. So, as you add components, they line up horizontally. When there's no more room on the current line, the next components automatically continue on the next line, still from left to right. And here's an important point. If you resize the container, the Flow Layout dynamically reflows the components. This means they might shift into fewer rows or more rows depending on the new width of the container. It makes the layout flexible and adaptable to different sizes. Every container has a default layout, but in our case, we're changing the layout for label frame to a flow layout. This is done on line 20, which is shown in figure 1.6. The set layout method, which we use to change layouts, is inherited by the label frame class indirectly from the container class. When calling set layout, the argument must be an object that implements the layout manager interface, like a flow layout object. So, on line 20, we create a new flow layout object and pass its reference as the argument to set layout. This way, we specify that the label frame should use the flow layout manager for arranging its components. Understanding this process is key because it shows how flexible and customizable our GUI design can be, especially when adapting to different display requirements. Let's talk about specifying the layout. The codes shown in figures 1.6 and 1.7 are used for two main purposes. First, for specifying the layout, which helps us determine how components are arranged inside a container. And second, for loading an image resource into our application. Now, when it comes to positioning components, there are two common approaches. The first is using a predefined layout. This allows the layout manager to decide where each component goes. It's a soft, flexible way of positioning, meaning if the container's size changes, the components will move accordingly. But keep in mind, this method might not give you the exact placement you want because you're relying on the layout manager's rules. On the other hand, the second approach is specifying the position directly using the container's coordinates. This is a hard way of positioning because you're manually setting the exact location of the component. This gives you precise control over where the component appears. However, the downside is that if the container size changes, the component's position will stay fixed, which might lead to layout issues. So, in summary, choosing between these methods depends on how much control you need versus how flexible your layout should be. Let's take a closer look at how we specify the layout when creating and displaying a label frame window. In this example, our class, LabelTest, creates an object of the label frame class on line 9. This is where the core of our window is set up. Now, by default, when you close a window in Java, it simply gets hidden. But in many cases, especially for main application windows, we want closing the window to actually terminate the entire application. That's what we accomplish with line 10. Here, we call the setDefaultCloseOperation method, which we inherit from JFrame, and we pass in JFrame, ExitOEnclose. This ensures that when the user closes the window, the whole program will exit. This line is crucial. Without it, closing the window wouldn't stop the application. It would just hide the window and keep running in the background. Next, on line 11, we specify the size of the window in pixels using setSize. This determines how wide and tall our window will be, giving us control over the layout and appearance. Finally, line 12 makes the window visible by calling setVisible with true. Until we do this, the window exists in memory, but isn't displayed on the screen. So, to summarize, this sequence of commands, setting the close operation, size, and visibility, are key steps in creating a well-behaved and properly displayed label frame window that aligns with the overall goal of building user-friendly GUI applications. Swing offers a really comprehensive set of classes for working with text within user interfaces. Because there's so much to cover, the creators of Swing decided to organize most of this text handling functionality into a dedicated package called JAVX, Swing, Text. This package contains dozens of interfaces and classes, along with 6 concrete component classes in JavaX, Swing itself. The result is a powerful and flexible collection of text models and components that are complex enough to support endless customization, yet simple enough to handle the common tasks easily. In terms of components, the Swing API provides several key classes that are either types of text fields or include text fields as part of their functionality. These include JTextField, which is used for single-line text input, JTextArea, which allows for multi-line text editing, and JPasswordField, designed specifically for password input where the text is masked for security. Overall, the important thing to remember is that Swing's text-related classes give us a lot of power and flexibility for building user-friendly interfaces that involve text input and display. They're designed to be both versatile and accessible, fitting seamlessly into your applications. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at Figure 1.8, which shows JTextFields and JPasswordFields. These are 2 fundamental components for user input in Java GUIs. JTextFields are used when you want the user to input a single line of text, like a name or an email address. They're simple but very versatile for many forms and data entry tasks. On the other hand, JPasswordFields are a specialized type of text field designed for sensitive information, such as passwords. They mask the input characters, usually with asterisks or dots, to keep the information private as it's entered. Both of these components are essential for creating interactive, user-friendly interfaces. They connect to the overall theme of building responsive GUIs that handle user data effectively and securely. Understanding how to implement and customize these fields is key to designing intuitive forms and login screens, which are common in many applications. Let's talk about event and event handling. Events typically come from user controls, meaning actions that the user performs or that objects trigger. For example, when you click a button, that generates an event. Another common scenario is when a user types something into a JText field or a JPassword field and then presses Enter. An event occurs at that moment. Now, our next example will show how a program can respond to that event by performing a specific task. The techniques we'll cover are actually applicable across all GUI components that generate events, not just text fields. In the examples shown in Figures 1.8 and 1.9, we use classes like JTextField and JPasswordField to create and manage 4 text fields. When the user types into any of those fields and presses Enter, the application responds by displaying a message dialog box containing exactly what the user typed. It's important to note that you can only type in the text field that currently has focus. When you click on a component, it receives focus, which means that's where your input will go. This focus mechanism is fundamental to how event handling works in GUIs because it determines which component will respond to user actions. Let's talk about event and event handling. This is a key concept because the text field that has focus is the one that generates an event when you press Enter. In this example, when you press Enter in the JPassword field, the password gets revealed. We'll start by discussing how we set up the GUI, and then we'll look at the event handling code that makes everything work. Lines 3 to 9 show the classes and interfaces we import for this example. These are essential for handling events and creating the GUI components. In our class, called TextFieldFrame, which extends JFrame, we declare 3 JTextField variables and a JPasswordField variable. You'll see these on lines 13 to 16. Each of these text fields is instantiated and added to the TextFieldFrame inside the constructor, which spans lines 19 to 47. Now, normally, when a user interacts with the GUI, they're telling the application what to do. For example, in an email app, clicking the Send button prompts the application to send your email. Similarly, in our example, pressing Enter in the password field triggers an event that reveals the password. This highlights the importance of event handling. It's how we make the interface responsive and interactive by tying user actions to specific responses. Let's talk about event and event handling in GUIs. GUIs are inherently event-driven, which means that they respond to user actions. When you interact with a GUI component, like clicking a button, typing in a text field, selecting a menu item, closing a window, or moving the mouse, these actions are considered events. These events are what drive the program to perform specific tasks. The code that responds to these events is called an event handler. Think of it as a specialized piece of code that gets triggered when a particular event occurs. The entire process of responding to these events is known as event handling. Now, let's consider two more GUI components that can generate events: JText fields and JPassword fields from the AWT SWING package. A JText field extends from JText component, which provides many useful features common to text-based components in Swing. JPassword field, on the other hand, extends JText field, but adds methods tailored specifically for handling passwords securely. Understanding how these components generate events and how we handle those events is key to creating responsive and interactive GUIs. It ties directly into our overall theme of building user-friendly applications that react seamlessly to user input. Let's talk about event and event handling. Each of these components, like a text area, is a single-line space where users can type text using the keyboard. Applications often display text in a JText field, which is straightforward. Now, when it comes to password input, we use a JPassword field. It shows that characters are being typed, but it hides the actual characters with an echo character, keeping passwords secure and private. It's important to remember that every input control, whether it's a button, slider, or another component, needs an event listener. If you want something to happen when the user interacts with a control, like changing a slider or clicking a button, you need to have a listener set up. Think of event sources as the things that generate events, like mouse clicks, key presses, menu selections, or even timers expiring. They are the sources of events that can happen in the UI. Some components are interested in these events. They want to react when something occurs. These components register themselves with the event source, so the source knows who to notify when the event happens. Those are the event listeners. In essence, this system of sources and listeners allows your application to respond dynamically to user actions and other events, making your GUI interactive and responsive. Connecting these ideas helps us understand how user interactions are captured and handled seamlessly in Java GUIs. Let's talk about event and event handling. To use events in Java, you first need to import the necessary packages. These include Java AWT, Event, JAWX Swing, and JAWX Swing, Event. These imports give us access to the classes and interfaces needed for handling user interactions. Now, there are several types of events you might encounter. The most common ones involve user controls like buttons, text fields, menu items, sliders, checkboxes, keys, and mouse actions. Each of these controls has specific listener interfaces and methods you use to respond to user actions. For example, with buttons or menu items, you typically add an action listener using the addActionListener method, and then implement the action performed method to define what happens when the user activates the control. Similarly, sliders use addChangeListener with the state changed method to detect changes in their position. Checkboxes, on the other hand, use addItemListener with item state changed to respond when their state changes. For keyboard input, you add a key listener and implement methods like key pressed, key released, and key typed to handle different key events. Mouse events are a bit more detailed. You add a mouse listener for clicks, enters, exits, presses, and releases, and a mouse motion listener for movements and drags. Each of these has specific methods, such as mouse clicked or mouse moved. Finally, for window events like closing a frame, you add a window listener with methods like window closing, ensuring your application responds appropriately when the user attempts to close the window. Overall, understanding these event types and their corresponding listener methods is essential for creating interactive, responsive Java GUI applications. Now, let's talk about the steps required to set event handling for a GUI component. In this example, we want to show a message dialog containing the text from a text field when the user presses enter. The first thing to understand is that before an application can respond to an event, we need to create a class that represents the event handler. This class must implement an appropriate interface, which is called an event listener interface. Next, we need to register this event handler so that the application knows which object to notify when the event occurs. Think of it like telling the program, "Hey, when this specific event happens, notify this handler." In our example, the class textFieldTest contains the main method, which is what runs the application. It creates an instance of textFieldFrame, which is the actual GUI window. So, to sum up, the key points are that you create a dedicated handler class implementing the right interface, and then you register that handler with the GUI component. This setup is fundamental for making interactive, event-driven applications responsive and user-friendly. Let's talk about event and event handling. On this slide, we see figure 1.9, which shows a test class for textFieldFrame. Now, the event object is really central here. It carries all the information about what just happened, like which component triggered the event, or any specific details the event listener might need to respond appropriately. So, think of the event object as a package of information about the incident. Next, the event listener is the object that listens for these events. When an event occurs, the event source, meaning the component or object that generated the event, alerts the listener. It's like a notification system. The listener then reacts by executing a method designed to handle that specific event. This interaction is fundamental to how GUIs respond to user actions. The event object provides the context, and the listener acts based on that context to update the interface or perform other tasks. This connection forms the backbone of event-driven programming, which is key to creating interactive applications. So, understanding these two concepts, the event object and the event listener, is essential for grasping how user interactions are managed behind the scenes. Now, let's talk about event and event handling. When an event occurs, a method of the event listener receives an event object, which contains all the details about that specific event. The event listener then uses this object to respond appropriately. This approach is known as the delegation event model, where the processing of an event is delegated to a specific object, called the event listener, within the application. If you look at the figure on the slide, you'll see that in line 42, the term handler refers to either the event object or the event handler object itself. From lines 43 to 46, you'll notice that text field 1, text field 2, text field 3, and password field are all acting as event listeners. It's important to remember that the class handling an event must implement the correct event listener interface. And a common mistake is forgetting to register an event handler object for a specific GUI component's event type. If you do that, events of that type will simply be ignored, which can cause unexpected behavior in your application. So, understanding this delegation model and making sure your event handlers are properly registered is key to ensuring your application's responsiveness and correctness. And with that, we come to the end of our chapter on adapter classes. I hope you've gained a clear understanding of how adapter classes serve as a bridge between incompatible interfaces, making it easier to integrate different components. Remember, the key points are about understanding their purpose, how they implement interfaces, and their role in promoting flexible, reusable code. This concept ties back into our overall theme of designing robust and adaptable software systems. Thank you for your attention, and I look forward to seeing how you'll apply these concepts in your projects.